Hello grade 12s. Today we're going to talk about sketching the graph of a cubic function. So this specifically I referred to already when we were talking about the factor and remainder theorem. So when we were solving cubic equations or third degree equations, I said the only reason we were solving third degree equations was specifically in order to find the x-intercepts of this cubic function or of this cubic graph. So a lot of stuff that we've done previously is now going to come together in this cubic function. So see if you can spot all the previous stuff that we discussed in the previous videos and how it pertains to this particular section. Right, so first thing we need to talk about is the form or the standard form of a cubic function. So the standard form of a cubic function is fx is equal to ax cubed plus bx squared plus cx plus d. So you'll notice there are some similarities between this one and the parabola or the quadratic function, clearly. But you'll see that what happens here is they just start with a being the coefficient of x cubed, b being the coefficient of x squared, c being the coefficient of x, and then d being your constant function. So I already discussed this when I showed you how to solve these cubic equations or the third degree equations using your calculator. I spoke about these coefficients of those different x's and then obviously the constant term. So this shouldn't be exactly strange. It should actually be kind of familiar after the previous discussions we've had. Now again, shout out to Lozandi, the Lozandi method. I'm going to show you first step by step how to sketch this graph of a cubic function, and then we will go and we will do a couple of examples just to make sure you understand what's going on. Now, normally when you sketch the graph of a cubic function in an exam, what they do is they actually scaffold it for you. So you'll see just now, you don't actually have to memorize these steps per se, because they will go and they'll ask you, for instance, in question 1a, please determine the x-intercepts. And then in, for instance, question 1b, determine the stationary points. So it's not like you have to memorize this, but let's just go through it step by step by step. So step 1, determine the x-intercepts, and that obviously is by setting fx equal to 0. Because any graph, if you want to find the x-intercepts, you make y, or in this case, fx equal to 0. Then, step 2, determine the y-intercept. So in order to determine the y-intercept, this is pretty easy and straightforward because that's just going to be my constant value. Logically speaking, if I make x equal to 0, all of these terms will become 0, and then only d will remain, so the y-intercept is the point 0d. Step 3, after drawing these cubic functions, determine the stationary points. Now this is very, very important, and that's one of the reasons we spend so much time in differentiating any type of function, but this is specifically going to be an easy differentiation because polynomial functions in general are very easy differentiation. So how do I determine the stationary points? This is something we have also discussed before. We determine the derivative and we set the derivative equal to 0. And that's pretty much because the gradient at any and all stationary points equal to 0. And again, I'm just going to reiterate, when I say derivative, you say gradient. So that means we get that derivative or the gradient function and we set that equal to 0. So that's how we're going to determine the stationary points. Now when you solve this particular equation, you will get an x value. But in order to get the y coordinate of the stationary point, we need to sub the answers back into that function of fx. Because please guys remember, the first derivative of fx gives you gradients, but fx gives you y coordinates. So this specifically is to get your y coordinates of those stationary points. So please don't forget that. Now, this step, I've put a little asterisk or a little star next to it because this is not always required. In fact, you almost never, ever have to indicate the point of inflection on these cubic function graphs unless they ask for it. So if they do go and they ask for the point of inflection, then yes, you do have to calculate it. But other than that, you can pretty much leave this step out. Now, in order to determine the point of inflection, and again, we've already spoken about this point of inflection in previous videos. The point of inflection is where the concavity changes, either from concave up to concave down, or from concave down to concave up. So pretty much that little point where concavity changes, or if the graph looks like that, that will point where the concavity changes. So from concave up to concave down, or in this case from concave down to concave up. That's your point of inflection. Now in order to determine that point of inflection, you have to set the second derivative equal to 0. So you set that second derivative equal to 0, you solve that equation, and then you sub the answer back into fx. And I should actually probably just cancel out this s. Because in general, the graphs we're going to be doing here, these cubic functions, do not have 2 points of inflection. They only have 1 point of inflection. So you will find that you will only get one answer there, and you only need to substitute the one answer back. Whereas stationary points, most of these cubic functions are going to have 2 stationary points. And you can see it from that shape that I have discussed before, where you have 2 stationary points, and you get those stationary points, and then you have to go and sub both of those x coordinates back into fx. So this one, yes, there will probably be 2 answers that needs to be substituted in. Then step 5, draw the graph. Now, a very useful little hack when you go and you draw these graphs is to actually know the shape based on the a value of that standard form. So if I go back to the standard form over there, a is the coefficient of x cubed. So when you look at a, the coefficient of x cubed, that will actually reveal the shape of the graph. Now, when we drew parabolas, when a was positive, the graph looked like this. And please note, I'm now going to show you the graph going from right to left and not the usual left to right, because this is going to be important to memorize the shapes of these graphs. So if I go and I say a is positive, I go from right to left and I show you that shape. But now what's going to happen is the following. We're going to go right to left, and then I'm just going to add an extra turning point. That would be the shape of a graph where a is greater than 0. And specifically, like I said, we draw that just like we would the parabola that's got a positive a value. We draw that part and we just add on that extra turning point. And then logically speaking, if a is negative, I do the same thing. But again, not going left to right, going from right to left. And I show that shape, which would normally be a parabola with a negative a value. But because it's a cubic function, I add that extra little turn. So right over there. Now, please remember these are not the only 2 possible shapes of that particular cubic function. So because these are not the only two possible shapes, you also have to be aware of this shape. There you go. And you also have to be aware of this shape. There you go. Now, this one particularly is a cubic function that instead of having 2 turning points, it only has 1 turning point. And this one as well, instead of having 2 turning points, this one only has 1 turning point. So if you ever go and you solve those stationary points over here, and instead of getting 2 values for your stationary points, you only get 1 value for the stationary point, the graph will not be shaped like this, the graph will be shaped like that. Now, they have asked these in previous exam papers, but this is very rare. Most common are these 2. Good. So let's do an example based on these steps, drawing one of these cubic functions. So the first cubic function is example 1 on page 230. Now, I'm not going to do it the way the example in the textbooks does it, where they scaffold it, where they go under A, do this, under B, do this. We'll do that with example 2. For now, we're just going to go and we're going to practice these steps that I showed you. So, first things first, step 1. According to the steps, we're going to say step 1, determine the x-intercepts. So, in order to determine the x-intercepts, I set fx, or I set the entire equation equal to 0. So, x cubed minus 6x squared plus 9x minus 4. And this is why we had that entire discussion about factor theorem or remainder theorem. So in my factor remainder theorem, we could go and we can find one of the factors and then factorize the rest. But I did show you guys, you can either go and you can use your silver calculator. So if you have the silver calculator, you can change it to equation mode, and we can just then go and select number 4, which is my cubic function, or cubic equation rather, and I can select 4 and I can type in the a value, which in this case is 1, the b value, which is negative 6, the c value, which is 9, and the d value, which is negative 4. And I can type that in and I will get my x-intercept. So the first x-intercept is x is equal to 4. The second one is x is equal to 1. And they only give me 2. Now, this might appear a little bit strange. Why? When normally in a cubic equation, we get 3 x-intercepts, do we only have 2 x-intercepts? Now, this is going to be very, very important for you to remember for these cubic graphs. A lot of the time what happens is the graph does not cut the x-axis 3 times. So if I draw an x-axis and I draw the shape of this graph, by the way, we can actually look at the shape of this graph saying A is positive. So because A is positive, I can then go and I can start over here and I can draw the graph like that. Now, if the graph were like that and this were the x-axis, I would have 1, 2, 3 x-intercepts. But sometimes what happens, and it just depends on the shape of this graph and also depends on my turning point. So once we get to the turning points, this will become nice and clear. It's possible that the graph could potentially look like this. There you go. Where over there, it turns on the x-axis. So because it turns on the x-axis, instead of giving you 1, 2 x-intercepts over there, it only gives you 1 x-intercept over there. And that's why we only end up having these 2 x-intercepts. And because we only have those 2 x-intercepts, we're going to have to go and look at the stationary points in order to determine which one of those 2 is not only an x-intercept, but also a stationary point. Okay, so that's then my x-intercepts. Next thing we have to do is you have to work out the y-intercept. So when we work out the y-intercept, we're just going to go and say it's the point 0, -4. So 0, -4 is my y-intercept. Step 3, we're going to determine the stationary points, or the turning points in this case. So stationary points, we first have to determine the derivative of fx. Okay, so the derivative of fx is equal to, and this is a pretty easy one, 3 times x squared, so 3 times x squared because we make the exponent 1 less, minus 2 times -6, which is -12x to the power of 1 plus 9, and then obviously the derivative of a constant is equal to 0. Now, I have discussed this, but you should know this. Please, please, people, they're very pedantic about this. They want you to show that you're setting that derivative equal to 0. A lot of people, they just go and they write equal and they continue down and then they suddenly solve the equation. If you don't write equal to 0, it's not an equation. And if it's not an equation, you can't solve it. So please, please, people, be careful to show that equal to 0 because they do give a mark for setting that derivative equal to 0. So now, in order to solve this, we're going to say, first take out the 3 as a common factor, which is then x squared minus 4x plus 3. Now obviously you could also use your silver calculator to solve this quadratic, but I think that's a little bit lazy. So I'm going to go and I'm going to just solve it by means of factorization. Now I'm going to divide by 3 just to get rid of that particular 3. So factorize the trinomial, saying it's x times x, and then it's going to be 3 times 1, and it's going to be minus 3 and minus 1, which means x is equal to 3 or x is equal to 1, which are my 2 x coordinates of the stationary points. Now please note, this is just the x coordinates, but what you should notice is you should notice this that I've already referred to. You should notice that over here when I solved the x-intercepts, we said 1 is one of my x-intercepts. So x equal to 1 is one of the x-intercepts. But now I found out, oh, 1 is also a stationary point. So this little shape is actually quite accurate. You're going to see just now, because here where x is equal to 1, not only do I have an x-intercept, I also have a stationary point. And over there where x is equal to 4, this is not a stationary point because obviously it doesn't appear over here. That is just an x-intercept. So that's what happened over here. That x equal to 1 is also a stationary point, and because it's also a stationary point, that's why I did not pick up 3 x-intercepts. I only picked up 2 x-intercepts. Right. Now I need to set these 2 points back into the original equation to get the y coordinates. So the first y coordinate is going to be equal to the f of 3, and the second y coordinate is going to be equal to the f of 1. Now, by the way, I'm not even going to do this calculation, and the reason I'm not going to do this calculation is because I already know x equal to 1 is my x-intercept. So I already know this is going to be equal to 0 because 1, 0 is my x-intercept and it's my turning point. So don't do extra work. Don't go and sub that entire point in there when you already know it's an x-intercept, so you know the y-coordinate has got to be equal to 0. Over here, however, we do have to do the calculation. So I'm going to go and I'm going to sub that into the original function. So please be careful. Do not sub it into my derivative. If you sub it into the derivative, you don't get a y-coordinate, you get a gradient. So please be careful what you do over here. So I'm going to sub 3, and I'm going to say it's 3 to the power of 3 minus 6 times 3 squared plus 9 times 3 minus 4. There we go. And that is going to give me negative 4. So that's my other stationary point, and this stationary point is then the point 3, negative 4. There we go. Now, because I know the shape of the graph, I can then go and I can almost roughly go and plot these points. So roughly plotting these points, I can say this is then the point 4, this is the point 1, which are my two x-intercepts. That's also going to be my turning point, which I've already indicated. And then I have another turning point over there, which is then the point 3, negative 4. So I can also put that in just because it makes the actual graph so much easier to draw just now. Now, like I said, we don't actually calculate the point of inflection. So over here at step 4, that little asterisk saying determine the point of inflection, that's only if they ask for it. You don't actually have to indicate it on the graph unless they ask for it. So in this particular example, I'm not going to calculate the point of inflection. I'm just going to use the data I already have to draw the graph. And also, please remember, the reason I'm going to draw the graph like this is because A is positive. A is equal to 1. And because A is positive, starting from right to left, I'm going to go and I'm going to draw the graph like that, and this is the shape that I'm going to be working with. And that is also why I drew this shape originally. So, next step, draw the graph. So, in order to draw this graph, we need to take all this information and we need to plot it as accurately as possible. It doesn't have to be perfect, but please, people, don't be sloppy with your graphs. So that's x and that is y. So we've got x equal to 1, and we've got x equal to 4, which are my x-intercepts. And please remember to indicate the coordinates, or at least just the x-coordinates of the points on the graph. Okay, so this is 1, and this is then 4. Then we know this is a turning point, so because I know this is a turning point and I know this is the shape of the graph, I'm just going to do that, just to remind myself it's got a turn there. And then we're going to go and we're going to indicate the other stationary point, which was the point 3, negative 4. So 1, 2, 3, 4. And that's the point 3, negative 4. Now, because this is not a point on the axis, we're going to go and we're going to put the coordinates in there. So good habits, people. If a point is not a point on any of the axes, please be sure to indicate the coordinates. Then I'm going to just quickly show the y-intercept, which is over here at negative 4. So that's negative 4. And then I'm ready to draw the graph. Might not be perfect, but that is pretty accurate. So that is your first cubic function. Congratulations with drawing that. I hope you followed along and you drew it yourself. So that is your first cubic function. Now we're also going to do example 2, but you'll see example 2, what they've done is they've scaffolded. So they've scaffolded it saying under A, determine all stationary points and use the first derivative test to decide on the nature of those stationary points. Now this is something you'll see is actually very, very easy to do, the first derivative test. Now generally in exams they do not ask you for the first derivative test. They don't do that. They might rather ask you to do the second derivative test, but we will discuss that in the next video. So I will show you the first derivative test quite quickly, and hopefully you'll understand it, but in general, they really don't ask it, so please don't stress too much about that. But we are going to calculate the stationary points. Now, the first thing you should notice is the following. F of x, in this example, is equal to minus x plus 1 cubed plus 8. Now what you need to notice about this is not in a format where you can find the derivative. Because remember, for stationary points, we need to find the derivative and we need to set it equal to 0. It's not in the right format because over there I've got a bracket cubed. And please, please people, you cannot find the derivative is if there's an exponent going on at a binomial, or in this case, if you think about it, it's a binomial times a binomial times a binomial, which means it's a product. We first have to simplify the algebra, which is a little bit annoying, but not too bad. So I'm going to go and I'm going to put the minus over here, and I'm going to say I've got x plus 1, and I'm going to split this up into x plus 1 times x plus 1 squared, because there's a shortcut for x plus 1 squared, which is x squared plus 2x plus 1. And there it comes down. Then I'm going to leave the minus out there. I will remember to distribute it just now, and I'm quickly going to go and do the multiplication over here. So x times x squared is x cubed, x times 2x is plus 2x squared, and x times 1 is plus x. And then again, 1 times x squared is x squared, 1 times 2x is plus 2x, and 1 times 1 is 1. And then finally, I can now go and I can add these like terms, I can distribute the negative, and I can add 8, which I'm going to do in pretty much one step. So I'm going to say it's minus x cubed. This is going to be 2x squared plus x squared, which is 3x squared, but I'm going to multiply by a negative, so it's negative 3x squared. This is going to be x plus 2x, which is 3x, but multiplied by a negative is negative 3x. And then over there I've got minus 1 plus 8, which is plus 7. So that is now in the correct format for me to find the derivative. So I'm going to go and say it's the first derivative of fx, which is my gradient function, and this is going to be minus 3x squared minus 6x minus 3. So that's my first derivative. And remember, stationary points set the first derivative equal to 0 so you can solve the equation. Now I'm going to take the minus 3 out as a common factor. So that's x squared plus 2x plus 1. And then I'm going to go and divide by that negative 3 just so it's not going to bug me now. And I'm going to factorize that, which is then going to be x plus 1 times x plus 1. Now, you guys need to note something here. This is very, very important. Now, instead of getting 2 stationary points, I end up with only getting 1 stationary point where x is equal to negative 1. Now, if you recall, in the shapes of the graph that I spoke to you guys about over here, we said when you draw the graph, these graphs, which are the more common ones, have 2 stationary points. But you can have a graph like this or a graph like this that has only 1 stationary point. So because I only have this 1 stationary point, I'm expecting the shape of the graph to look like this. Okay, so I'm just going to remind myself that it is possible to only have that 1 stationary point. Now I do need to get the y-coordinate of the stationary point, so the y-coordinate of the stationary point is then f of negative 1. So I'm going to quickly just use my calculator to substitute in. Now by the way, you could use this version, or you can just go back to the original version. So you can go and say it's minus x, which is negative 1, so minus 1 plus 1 to the power of 3, which you can actually notice that's going to be 0. So when I add the 8, I know the answer is actually going to be 8. So that means my stationary point is going to be the point negative 1, 8. There we go. Now, this first derivative test that they spoke about, really not that complicated. Pretty much all that's going to happen is the following. You're going to go and you're going to say, I'm going to look at the point negative 1, which is my stationary point. And then I'm going to look at a point just before negative 1. So just before negative 1 is the point negative 2. And I'm going to look at a point just after negative 1, which is the point 0. And I'm again going to use my calculator to just type in these values. And very, very important, they set the first derivative test. So the first derivative test means we're going to sub these values not into fx, we're going to sub it into the first derivative. And you'll see what happens just now. Now careful when you sub it into the first derivative, not this version over there, always the original version. So I'm going to say table mode minus 3x squared minus 6x minus 3. There we go. And I'm going to start at negative 2, I'm going to end at 0, and I'm going to step in ones. So what I need you to notice is the following. Where x is negative 2, fx, but careful, we didn't type in fx, we typed in the derivative of fx here. So this is actually the derivative. So the derivative here is negative. And there it's 0, as to be expected. And there the derivative is also negative. So what we have here is we have the gradients, because remember, if I sub into the derivative, I get the gradient of the graph. So in this particular graph, before my stationary point, the gradient is negative, so it's decreasing. And then after my stationary point, the gradient is still negative, so it's decreasing, which refers to that shape. So that shape just says it's a decreasing function, then I've got a zero gradient, and then it's a decreasing function again. So this just tells you, because it doesn't go from positive to negative or negative to positive, it's not a turning point. This is actually a point of horizontal inflection, which is something that I have referred to previously. Okay. Now, the next step in this example, they asked determine the intercepts with axes. So in order to determine the intercepts with axes, again, I'm going to set my equation minus x plus 1 cubed plus 8 equal to 0. And I'm using this format of the graph just because it's easier to solve this. Because I can then go and say 8 is equal to x plus 1 cubed. There we go. And then I can use a cube root over there, and I can use a cube root over there, which then means x plus 1 is equal to 2. Now please note, there's no plus minus there because this is a cube root. So if it's a cube root, we have to remember whatever's inside. If it's positive, the answer is only positive. If it's negative, the answer is only negative. So to finish off, x is then equal to 2 minus 1, which is 1. So that is my only intercept with axes. Instead of having 3 or even 2, I now only have 1 intercept with axis, which is also possible. Definitely possible. Then to get my y-intercept, so this was my x-intercept. So in order to get my y-intercept, I'm then going to go and I'm going to set x equal to 0. So the f of 0 is then equal to minus 0 plus 1 cubed plus 8. There we go. And that's then going to be equal to minus 1 plus 8, which is 7. So my y-intercept is the 0.07. There we go. So the next question says, draw the graph. Now in order to draw the graph over here, again, we're going to draw these axes. I'm going to try and be as accurate as I possibly can. That isn't always possible, but we'll see how it goes. So first things first, I'm going to indicate the stationary point, and the stationary point is at negative 1, 8. So there's negative 1, and there's 1, 2, it's supposed to go up 8. 1, 2, 3, 4, 6. Make that a little bit longer. So 1, 2, 3, 4, 5, 6, 7, 8. So right there, I've got that point, negative 1, 8, which is my stationary point. Then I'm going to go and I'm going to indicate my x-intercept, which is over here at 1. So right there at 1. And then I'm going to indicate my y-intercept, which is going to be over here at 7. And then I'm going to try and stick to that shape that I showed you at the beginning, which allows me to go through these points. And that is then this particular graph. No, not very pretty, but as long as you have your axes scaled, so your x-axis and your y-axis, as long as you have it scaled and you indicate any points on the axes and you also indicate in coordinate form any point not on the axis, they don't really have a problem if it's not 100% accurate. So thank you very much for listening.